All right, let's take a look at this example of an acid-base reaction, and we're going to apply to it the new general structure that I just showed you on the previous slide. So we should recognize that this is still a double replacement reaction. This is still an acid-base reaction, but this time it's even more specific because instead of cation being anything, it's going to be hydrogen. So there's my H. My anion here is going to be my A. I called the spectator ion here sodium X, and then the base here is going to be B. So HCl here is going to be your Bronsted-Lowry acid, because you can clearly see that this hydrogen is going to end up donating itself to OH. And because hydrogen only has one proton, we say that the hydrogen is donating its proton to the OH, hence making your hydrogen with your base attached to it, and it now has an extra proton. That's why we put the plus there. And you'll notice that this is now water, acid-base neutralization reaction. You'll notice on this side, my spectator ion, sodium is hanging out right there. And now I've got my A hanging out by itself. Well, if we were to do the same form as we've been doing before with double replacement reactions, you would have just written NaCl for salt. But if you've ever put salt in water, you know it dissolves. When something dissolves, it splits into its ions. So you'll see here that now I've got A all by itself like that. And so we put a negative charge there to show us that that's the anion. So let's take a moment and define which of these new species is going to be what we call a conjugate acid and a conjugate base. So you'll see here that now this water has this extra proton. Having an extra proton has now changed water into what we call a conjugate acid, meaning it's what happens after the water accepts a proton. And since now that water's accepted a proton, it has an extra proton it could give away back in the other reversible direction. So it's now your conjugate acid. Your conjugate base is going to be the Cl. It can, in equilibrium in the reverse process, accept a proton and be remade into HCl. And then Na here, it's just going to hang out. It's a spectator ion. It's just going to hang out suspended in the solution, and we really just don't pay much attention to it. Really important to notice that this reaction is reversible. So if I can go forward here and make water and a conjugate base with chlorine with the -1 charge, I can also go the opposite direction where these species can reform into HCl and NaOH. And you might see where we're going with this, that we can calculate an equilibrium constant for this one. So that's example number 1.